Okay guys, so let's get some programming. Okay, I was actually done with these summary ranges. Am I signed in, right? Okay. So I want to find a better solution to that. Let's see, sign me in, sign me in. I need to sign in with Google. Um, okay. Okay, so I had completed summary ranges. Okay, so I would just go and where are the solutions, man? There used to be solutions. There's solutions. Um, okay, there we go.
Hey guys, Greg here. Let's solve summary
So,
ranges, LeetCode number 228.
so
So we're
let's take
given
a look
a
at this.
sorted unique integer array called nums, and we're defining a range as square brackets a to b. And this is the set of all integers from a to b inclusive. So it's a to b including a and b as well. So we need to return the smallest sorted list of ranges that cover all the numbers in the array exactly. Now this doesn't really mean anything unless you look at the example here. So basically it wants you to return this. If you have 0, 1, 2, 4, 5, 7, then you have 0 to 2, so we have 0 to 2, but then there's a gap there, so we're missing 3, so then it's actually going to be 4 to 5, because we're also missing 6, and then we have just 7. So basically, it's the intervals of A to B of the stuff that we have, and if you have just one number in a row, there's nothing before this and nothing after it, then it's just going to be that number by itself. So basically, we're going to have an index I, which is set to the first index, and we're also going to be building up a new array, which I will just call our answer. That's going to start as an empty array. Now we're going to get a starting value, which is going to be the number that we're looking at right now, which is going to be 0. Okay, so we're looking at this number here. Now you want to ask the question, is the next number, aka what's at I plus 1, this number here, is that what you're expecting, which is nums at I?
So I do that, right? I just use I. Okay, I don't do that exactly
Plus
like
1.
that.
Well, no, it's not. This is not the value of 1, and so we basically have a break here. So we're immediately ready to plug something into our output array. What is it going to be? Well, it's obviously going to start at 0, and actually our starting value is that same number that our array is still looking at. So basically meaning that we didn't move at all. So we're actually just going to keep it as just 0. You can think about this as the string is 0, but I'm just going to write it like that. So then we'd look at the next number here, and we'd say our starting point is then 2. Okay, is the next number over the one we'd expect? Yes, it actually is. So in that case, we're really just going to move over our index and look for a break. We do not update our starting point because our current starting point was still that 2. We keep moving this over, and then here we see that there's actually a breakage on the next number. So our starting point was what we started at. That's why we marked it. Now we're going up until our current number. So the starting point is not what we're currently looking at, meaning we actually covered some ground here. We're ready to plug something into our output, and so you'd want to get our starting point and then up until our current value. Okay, we're going to move this index over. We'd see that we actually have a starting point of 6, and immediately we have a breaking point. And so you are ready to just plug 6 into the output because our starting point is matching our current value. Over here, we see 8. There is no breaking point, so we are going to start at 8, and we are going to keep this going. Here, this is the other situation that you can consider a break because we don't have anything at the end of the array here. You need to watch out for that out of bounds error. So there's nothing over here to the right, meaning we must be done here. Therefore, same rule, we started at 8, we're going up until 9, and so we are going to go from 8 up until 9. So you could ultimately return your answer once you got to the end of the array, and that's really all there is to it. Okay, so we'll get an empty array, which we're going to call answer, and we'll set our index I equal to 0. Now, while I is less than the the length of the nums, we'll get our starting point is equal to the number
Month
we're
of
currently looking at, nums at I. Then while we have I is less than the length of nums minus 1, so this makes sure that we are not going to look out of bounds because we're trying to look over at I plus 1. So
Okay.
now we can look at I plus 1. If we have this as the case and that our current number plus 1 is equal to our next number over, well, that means we don't have a break. So we want to
Okay.
just increment I. So he's going to keep going while this stuff is true. After we get out of this while loop here, we have hit a breaking point. Now we just need to know, do we want an interval range or do we want just a single number? You want the single number if your starting value is still equal to whatever nums at I is currently. So if
Okay.
start is not equal to nums at I, that means that you did actually cover some ground here. We'd want to answer.append the interval, which is the string version of start, plus the string of the arrow, so we can just draw it with a dash and then that bracket like that. And then it is going to end in the string of the current nums at I, which we know is going to be a different number than our starting point because we've already checked that. So that's the case if we have an interval. Otherwise, we don't have an interval because
Now we
start
simply
is just equal to nums at
I.
so it's just one value. We would answer.append with
String
string
of
of nums
number
at
of I.
And after this loop is done here, you would want to I plus equals 1 and ultimately return your answer. Now let me answer one question you likely have, which is, hey, isn't this an n squared time complexity? You have a while loop and then within that you have another while loop. Well, no, because this while loop, that is going to end when I gets to the end of the array. Okay, this one would too, but I is not getting reset, okay? It would be n squared if you basically had I going over the array, and then you had some j value that was kind of going up and then getting reset, and then going up and getting reset. That's not the case.
Okay.
I is steadily moving towards the end of the array, and so as long as that is the case, this is going to be a time complexity of big O of n, where n is the number of elements of nums, and the space complexity here, you could
O
either
of
call this
what?
O of
Of
n
n.
to store the space, or you could call this O of 1, kind of ignoring the space that the output has. Sometimes people would ignore that because it is the answer, but for us, we're just going to say this is O of n, because most people would...
Okay. So basically, too much spaghetti code here. And I hope I have stored the solution, the current solution. If not, then I should. Let's go here and go to what was it? Data structure and algorithm, GitHub. Use the LeetCode and algo maps and strings, summary ranges. Then say ni algo solution dot py. Right, so just open it. Okay, so before I think I solved it here. No? No. Okay, so main 2, there's nothing in main 2. Something here. Yeah, I think it kind of worked, but it was not the solution, and I think this is the part. Yep, this is the part where I did it all. Okay, so I'll go LeetCode 228. Right. Okay, I'll come back to this. So I want to delete up to here. Okay, so we will make an empty list answer, and then we will have I initialize I equals 0, then while I is less than len of nums. Okay, we want to iterate up to the end, then we say that start variable equals nums of I. Then we want to check two conditions: while I is less than len of nums minus 1, alright, and given that the next number from I is just the difference between the current number and the next number is 1. So nums of I plus 1 equals nums of I plus 1, right? If so is the case, we simply increment I, right? And when we come out of the loop, we want to check if the number we are at and the number we started at are the same, right? We want to check if um, start equals, okay, if it is not equal to nums of I, then we will append start plus nums of I. Okay, and if so, and if it is not the case, then what happened here is that we simply that the start and nums are same, so there is only a single number which we can append in the answer. So str start sorry, nums of I, or start maybe, but I think nums of I is it better, less than len of I n minus 1. Okay, we'll see. And then when we come out of this loop, I want to increment I to 1, and at the end we return our answer. So let's try and run it. Unknown network, please try reloading the page. Okay. Oh no. Okay, sign in. Let's see. Okay, so let's try and run it. And okay, it gets accepted, right? So I 7. Okay, we increment I regardless, right? So in this case, um, and this is outside. Okay, because this is outside of the loop, we can simply indeed if these I and they both are same. Okay, and we submit it. Okay, great. This is runtime and memory. Ooh, there are few less solutions with less memory. Summary while okay, if not nums return this. If a equals 0, summary is this, while a is len of num start, we start. This is the same. Then why does this take less memory? Done summary. Format. Okay, that's okay. Right. Okay. So that is done. So let me just copy this. Just copy this function. Sorry, mine. How can I get my solution code? Yes, okay, thank you. There we go. Okay. Okay, so this shows our answer. Protecting from index out of bound, we create a start variable holds the value at beginning of the loop. Then here we check two values. Here we check two conditions. First is that since we are looking ahead by 1, you want to make sure that I is within bounds, and hence we limit it to len of nums minus 1. The second is we want to make sure the numbers are consecutive. So we check nums of I plus 1 equals nums of I plus 1. Okay, now and we keep incrementing I until these conditions are satisfied. When we come out of the inner loop, we want to check if we are where we started. That is, if nums of I equals to start or not. If it's not, we append a range, and if they are indeed the same, we append the single variable. And at the end of the loop, we increment I again. Okay, so this is it. Alright, so I have completed this. So let's get on to hash maps. And do you want to take a revision? Let's take a revision. Okay.
Hey guys, Greg here. Let's talk about hash tables. So that means hash functions, sets, and maps.
Okay.
So let me draw a hash table. Now it's going to look fairly similar to an array for now, but it is quite different in many ways, and we'll see why. So basically we have 5 positions here, and I'm drawing little boxes here, which you can kind of think about as buckets. So this is going to be bucket number 0, bucket 1, and so on. Now let's say we had the string of Greg, and we wanted to put that in the hash table. Well, to put something in the hash hash table, we need to hash it, which basically means that you need to apply a hash function to this, which is going to take your input. In this example, it's a string, but lots of things are hashable. We'll see what is later. So our hash function is going to take our string and it's going to output an index. It's got to be a number 0 through 4 here. Now, there's lots of different hash functions that exist. There's kind of an infinite number of them. Some are better than others. But one we'll think of, which is kind of simple, is just thinking about the alphabet's ordering. So G happens to be the 7th letter, E is going to be the 5th letter, and I just have this memorized here. R is actually the 18th letter. So if we know that this is true, well, then we'll think about this as a 7, this is an 18, this is a 5, and another 7. If we take all of those things and then we sum them together, that turns out to be a sum of 37. Now, that's way too big, but that's totally fine because you can just mod it or take the remainder by the number of buckets or positions that we have. So we have 5 positions in this hash table. If we mod it by 5, you're going to get a number that's 0 through 4. So we mod it by 5, and we're going to get the position of 2. So that basically tells us that we would put Greg in this position right here. And if you wanted to put something else in the hash table, we'll say a name of Gre. People call me that as a joke. So Gre is just going to be that number subtract 7. So that's going to be a sum of 30. And you mod that by 5, you're going to get actually 0. So that tells you that Gre is going to go over here in the hash table. Now, what's very interesting about this is that you can actually have what's called a collision. And so if you had the string of Gerd, so GRG, well, that is going to be 7 plus 18 plus another 7. That is going to be a sum of 32. And mod that by 5, you're going to get 2. So hash functions, or hashing in general, can have collisions because you don't have that many buckets here. We have so many different strings that are possible, but you have the limited number, in this case, just 5 many buckets. So what do we do when Gerd also belongs in this bucket right here? Now, there's basically 2 different methods you would have when you run into these sort of collisions.
Open
the first one is
chain
actually
and
very
close
simple. This is going to be a
chain.
method which I'll write in a corner over here. This is going to be called separate chaining. So basically meaning that each of the buckets or each of the positions in the hash table, they're all going to be basically separate chains. And by chain, we basically just mean linked list. So that basically just means store these things in here, and we're going to have each of them be a linked list. And you can think of each of the individual components as linked list nodes as well. This is just a linked list with one element. So that way, if you ever ran into a collision, we'll just say, for example, that Joe, I actually don't know what the index is, but we'll say that it maps to this one right here. Well, if there's already something in it, well, then you can basically just keep this chain going. So we can add Joe over here. Now, why do hash tables even exist in the first place? What's the purpose of this data structure right here? Well, the main point is to implement one of these 2 things, which is either a hash set or a hash map. And for now, we'll stick to hash sets. So a set in general is basically a collection of unique items, and so a hash set is
Unique
a set that
items.
uses hashing. And the reason that hashing is generally a nice thing to do is because if you wanted to look up, say, is GRE in this hash table, is it in this hash set? Well, then you could do that in constant or O of 1 time, which means that if this hash table had a million things in it, if it had, n equals a million things in it, well, then it's still constant time to compute the hash function on the string and just to immediately look up its corresponding index. All of this other stuff, all of the other positions here, they really don't matter at all. And so regardless of how many things are in the hash table, you just look up that one index in constant time. And by the way, for a clarification, people often get confused here. By O of 1, we mean it's constant in relation to n, where n is like the number of things you've put in the hash table. Generally, to hash something, if you have a string of, 3 different characters here, it is going to have to go over the string. It would be kind of O of s, where s is the length of the string, but in terms of the entire thing that exists here, it's going to be constant in relation to n. Now, unfortunately, this is only kind of partially true, which is why you might be tempted to draw an asterisk here and add the word amortized, which essentially means on average. Because as you can see here, if you wanted to check if Greg is in this hash set, well, then you would get the index of 2, and you'd see, okay, well, it's at the beginning of this linked list. But if you wanted to ask, say, if Joe is in here, well, it would go to this index, and we have to go through the linked list. And so you would, at the end of this list, find that Joe exists. However, this is in relation to n here. So if you had a bunch of stuff in the table, or particularly a bunch of stuff, we'll just draw some letters here to make it quick. So the math turns out so that on average, it's going to be constant because assuming a good hash function, you'll have these names kind of distributed throughout the hash table and not stuck in the same linked list. But because that list does exist here, you could, at the very, very worst case, absurdly unlikely, but technically possible, all of the n things could be in this linked list. And to traverse that, this would be in the very, very worst case in O of n lookup. But what you'd write here is on average, assuming a good hash function, it's going to be roughly constant time. So that's basically what a hash set is. All you would really do is one of 3 things. You would look up if something exists in there. So you'd be like, is Greg in there? Okay, cool. You can do that in on average O of 1 time. You could add into the hash set. So maybe we're adding someone like, we'll call him Jeff here, and maybe that maps to the 1 index. I'm not really worrying about the correct index here, but if you did that, that's going to take
constant time.
O of 1 time to do that. Or what would happen if there was something else in the linked list is you would kind of make that the new head. So you could also do kind of something like that, which is still going to be constant time. You can also delete stuff, otherwise called remove from the set, and that's going to take, again, on average, that's going to take O of 1 time. Because if you wanted to say remove Joe from here, well, you'd have to hash it to get that index, and then you would have to traverse the linked list and find it, and then you'd remove it. So again, that's kind of going to be roughly O of 1 time. Okay, so that's how to use a hash set. Now let's show you how to use hash maps. Now a hash map is basically all the functionality of a hash set, except it can store data. That's the main point of it. So let's say we had a string of Greg here again, and to use the terminology for hash maps, this would be called a key, and you'd be mapping them over to values. So keys can map over to values.
Key and values.
It just allows you to store data associated with the key. So we have Greg is going to map over to, let's say, his favorite number, which is 7. Now it's important to know that keys must be hashable, and we'll talk in a few minutes about things that aren't hashable and why they're hashable and things that are not. But the values are pretty much anything. You could store really any data associated with this at all. Any data type supported in the language is totally fine. So let's use that same function as before, which is going to get a sum of 37. If you mod that by the number of buckets we have, we get the position of 2. So basically, instead of just kind of storing Greg here, you would basically just store Greg along with the data. So you can make basically like a slightly different linked list that allows you to have kind of multiple things. The first thing would be the key, and the second thing would be the data that you're storing. So we'll just make that basically a tuple of 2 values, and that's going to be, say, a linked list node. Again, this is if we're using separate chaining. I'll show you how to use a different technique in a moment. Okay, so basically we just store Greg with his value of 7 in there, and if we had, say, Gre, that's going to get mapped, as we saw, to the position of 0. And so maybe Gre's favorite number was 5. So that basically just stored Gre with the value of 5 here. Now for lookup, there's kind of 2 things you might want to do. You might want to see just if a certain key is in here at all. So if GRE is in here, that would be just a true-false question, and that would return true. Or what lookup could mean is basically return the value associated with the key. So if we call this thing H, for example, then you could basically write something like this, like what is H at GRE, and that would tell you that the value associated with the key is going to be 5. Again, you can have add, which is going to take, roughly O of 1 constant time, because you just want to add a new key value pair in here. So maybe you had the index of Joe, and so he's just going to map, say, Joe to 1 in here, and that's going to take a constant time to add a new key value pair. And remove, this is again going to be on average, that's going to be O of 1 time. That would be removing a certain key, and in Python you might write this like something like del for delete the hash map at GRE. This removes the key that you're looking for here, and that would just remove that key value pair from the hash map. And again, that's going to do that in roughly constant time. So those are the main things you want to do with hash maps and hash sets. But now I'm going to show you a different technique to handle collisions, which is known as linear probing, and it's really not too bad. So for this example, we'll just use a hash set, although it will work exactly the same way for a hash map. Okay, so let's say again we had the string of Greg, and you compute its hash function 37. You mod that by the number of positions that we have.
We use another hash
function. Same thing for
function.
now. We're going to put that into the hash table, and if you were to add GRE, that's going to be the same stuff as before. Put that into the first position. But now if you had just the silly name of GR, well, that's going to have 24 35, and so that is going to have the same position as GRE. Now we're not going to make this a linked list or any sort of collection of items. We're not going to chain it up in this position. We're going to find a different position in the hash table. So basically what you would do is you keep just off checking by 1. So if it went here, but that was already full, well then you would check over here, and you would see that it is empty. So basically it would just put GR in this position. Okay, then if we had, say, GERG, so GRG, well, that's going to add 7 to this, so this is going to be 32, and mod by 2, this is going to go to the position of 2. And since this is already full, then we're going to look for the next position, and that is actually empty right here. Now this still supports the same operations as a hash set and a hash map. You basically have hash tables are going to implement hash sets and hash maps. So for lookup, basically what you would do here is compute that index via the hash function. You would look up that spot, and you would see, oh, that's not actually what we were expecting. Is it over here? Yes, it is over here, and so you'd return true for that because you did find it. But if you wanted to know is just G in the hash table, so that's going to have a sum of 7, which is going to get modded again to 2. Well, that's going to say, hey, is G over here? No, it's not.
No.
Okay, is it the next one? No, G
No.
is not here. Okay, is it over here? No, we hit a blank, and that's basically when you would return false here, which says that G is not in the hash set because you looked for it and we did the linear probing. This is the linear probing here, and since we hit an empty element, we determine it's not there. Now you can kind of see we had a similar issue as before, as we're not truly constant time here because you're looking here, but then you're going over here, and you're kind of bouncing between things. So for the same reason, we're still going to have basically a worst case of O of n when we're looking something up, but for the most part, on average, you're still going to get an O of 1 time here. Now if you wanted to delete the key of Greg in here, so GREG, you get your hash function, and so you get your total of 37, you mod that by 5, you get your position of 2. You look over here, and you say, okay, cool, we're ready to delete that, that's totally fine. But this might break our probing because we're kind of relying on the other positions to locate stuff. So if you wanted to look up GRG, if you wanted to see if GRG is in here, well then you would get your position, which is going to get 32 mod 5, which is 2, and you'd see, you kind of conclude that it's not there. But that's not true, it is there. So when you delete, basically all you need to do is instead of kind of leaving a gap, you need to mark it by something special, like say a -1. That way it just means that we know something was there. It basically tells us to do our linear probing. So if we look over here, we see, okay, now we do have GRG, we basically return true that it is in there. Okay, so that's linear probing. It's a little weird to me, and I definitely prefer the separate chaining technique, but either one you do there, basically everything you do is going to be roughly constant time to look up if something's there, to remove something, to add something. All of this stuff is going to be, roughly, it's going to be constant time. And so that's why these data structures questions often use either hash sets or hash maps because they have a very fast lookup. So if you had like a string of a million things here, we had a million things in this string here, and it's equal to a million things. Well, then if you were to look up if a certain letter is in this string, well, that's going to take O of n, or basically a million time. But if this was instead a hash set, well, then it would actually be constant time to look up in that. Okay, so you're going to see these come up a lot because of that fast time. Okay, before we do any coding, we have to have the conversation of what is hashable. So what different data types are hashable? Obviously, strings are because we've been hashing on them a lot. Another data type that's hashable is integers, so those could be the keys of a hash set or hash map. You can also make tuples hashable, so that's going to be stuff like this, like the tuple of 1, 2, 3. That's otherwise called a frozen array. And I'm going to make a little table here. So on the left here, these are the things that are hashable. Okay, and this is opposite to what is not hashable. And this isn't going to be a complete list here. It's just going to give the idea. So some things that are not hashable are things like arrays, or in Python, is going to be dynamic arrays or lists. And dictionaries are something that are not hashable. And dictionaries are basically hash maps themselves. So although dictionaries or hash maps kind of use hashing, they're not actually hashable themselves. So you can't make a hash map a key for another hash map. Okay, and there's lots of other stuff here as well. But basically what this boils down to is that these things are immutable. So they're objects that you can't change the underlying memory of. That's what immutable means. And these are things that are mutable. So these are things that you can change the memory of. So you can say like, hey, for an array that has the positions of 0, 1, 2, you can after the fact say something like, okay, actually,
so
let's set a
immutable
1
things
to
are
be a 7,
hashable.
and that would change the memory to be a 7. So because that's allowed, it means that it's mutable. And that is basically the reason that it's not hashable. So things that are hashable are immutable objects, and things that are not hashable are mutable objects. Now just to give a little bit of a reason to this, it's basically because you want to ensure consistency in your hash table. So if you were trying to hash something like the string of Greg, well then that's a string, which is immutable. This is always going to be exactly the same. So whether you hash it now or in the future or whenever, it's always going to output that same index, which for us that was mapping to the index of 2. Let's say for example that strings were mutable. Well, if we were allowed to do something like this, change this to be an F, that actually would make this be a different position. And so because that's the case, you would want consistency. You want the same object to map to the same index. But if that object is mutable, you're allowing the same object to map to a different index. So that's why that's not allowed. And so you can only hash things, aka make them keys in a hash set or a hash map. You can only make these things keys if they are strings or integers or tuples or anything that is immutable. Anything that is mutable, that's not going to work. Okay, so that's the main theory. Now let's show how to use these things in Python. Okay, so let's first talk about hash sets. So in Python, you would make a set, give it a variable name, and just make it an empty set like this. And then you could just over time add things into that set. So for right now, we would just
Dot
print that,
add.
and it's going to show
S
now.
dot
So we
add.
start adding things into the set. This is going to take in on average of 1 time. Pretty much all of this stuff is going to be constant. That's the point. So we call s.add. There's lots of things that are hashable. Here we'll use integers. So we'll make a set of integers. We'll add 1 into the set. We'll also add a few different things here. Add 1, add 2. We'll also add 3. And if you were to print s, it's going to show that we have 3 different things in the set. So look up if item is in the set, and that's going to take in on average of 1 time. So you can do that with something like an if 1 is in the set s. Well, if that's true, this is going to execute. So we just do something like print true. 1 is in the set, so that's going to be true. If you did something like if 1 not in the set, that's going to be the opposite because 1 is in the set. That's still going to be an O of 1 lookup operation, and that's why these things are so good. So really the only other thing that you would do with a set is remove something from the set. So s.remove a particular element. If you try to remove something that didn't exist, like 4, it's actually going to throw an error because that key is not in the hash set. So if you s.remove something that is in the set, that's going to take a constant time. And if you were to again print that set afterwards, it will show that 3 has been removed from the set. So maybe you had some long string of a bunch of characters, and maybe there's even a bunch of duplicates. Maybe it looks something like this. If you had a problem where you needed to know if a character is in here, if you needed to know that multiple times in a row, you needed to keep looking up into this string. But that's going to be very, very slow. What you can do is make a set sett is equal to a set of that string. And this is going to take O of s time. So you could call this basically just a set construction here. And so what that would do is basically just have the set of all the unique elements. Because the point of a set in general is that it has only unique things here. We want to check if things are in the set. So you don't need to have a twice or b twice.
Only
so
unique
anything
things.
like looking up if the item is in the set, that's all going to be constant time with regards to the size of that set. And really that's all you'd ever want to do with a set. In a very rare but occasional circumstance, you might want to loop through the elements in the set. So we could do something like for x in the set s, then you could print the element x. You could do that, and that's going to be an O of n operation because you're explicitly looping over everything in the set, and that's definitely going to be an O of n time, where again n is the number of things in the set. But this is not really a fundamental set operation. That's just something you might do at a convenience. Okay, now let's move on to hash maps, which in Python are just known as dictionaries. Okay, so we'll make a dictionary, just call it D, and you would immediately write squiggly braces like this, and within here you would put all the key value pairs that you want. So again, there's lots of things that you could hash, so the keys could be lots of different things, but we'll make them strings here. And the values you can map pretty much over to anything. So for now we'll just make them integers, but these could be, lists of integers, they could be, nested lists of integers. It really doesn't matter what you map over to. These are very versatile, and so they can store whatever data along with the key that you want. So Greg maps over to 1, Steve maps over to 2, Rob maps over to 3. If you were to print that, that's just going to look exactly the same way. You could add a key to value pair in the dictionary, and that is going to be a constant time thing to do because it's just using hashing. So we would do that with d at a new key. So we'll say d at arch, that is equal to 4. And if you were to print that, that's going to reflect that change. So that's again constant time. You could do a lookup. So this is just wondering if a certain key is in the dictionary. We don't really care about the value. This is also going to be a constant thing to do. This would be like an if statement. So if Greg is in the dictionary D, then we could print true. So if you did that, well, that's going to be true because Greg is in the dictionary. That's a constant time lookup. And you could also do the opposite. So if Greg is not in the dictionary, then you could run something. Okay, and very similarly, instead of checking for presence of key, so that's just a base true false lookup, you could also check the value corresponding to a key in the dictionary. And that's again going to be O of 1 or constant time. You could do that with, say, D at Greg, and that is going to basically fetch the value associated with this key. And if you were to print that, you'll just see the value, which is going to be 1. So that's the value corresponding to Greg. And it's important to know that if you use this syntax here, you're kind of assuming that this key is in the dictionary. Because if this key is not in the dictionary, so basically D at GRE, that is not in here, well, this is actually going to throw a key error similar to how that set deletion thing did. So if you're ever looking up the value of a key, you need to kind of run this if statement first to make sure that, Greg is in the dictionary. Okay, yes it is. And now we're kind of able to do this because we know that that key is in the dictionary. Now, just as we kind of looped through the set here, you could definitely loop through a dictionary as well. And I'd say that's a little more common. So we could loop over the key to value pairs. Generally, you say the term the key value pairs of the dictionary. That's going to be an O of n thing to do, where n is the number of key value pairs in the dictionary. There's multiple different ways, but the way I usually do it is for key and value in the d.items. So that is going to get each of the keys and values. If you are to print it, I'll just print it in the same way it would look here. Key over to the value, and we can actually make this an f string to print it really well. We put the key over here, and the value is going to be the val. So if you were to do that, it's going to say that the first key is Greg with the value of 1 is associated with value 2, and so on. So that just loops over those n things. Now, because hash maps in particular are so common in Python and data structures in general, there's actually kind of a few clever ones that exist. Now, one of them is called a default dict. And you would import this generally you would do from collections. You would import the thing called default dict. So if you made a default dict, we'll just call it default. You would write default dict, and then what you would do here is pass the thing you want as a default. If you were to pass, say, the type of integer, it looks a little weird here. Basically, the default integer is the value of 0. It's just the simplest integer. So if you were to do something like default at the key of 2, we haven't put any key value pairs in the dictionary. But if you were to run this, it's going to say 0. So basically, if you did this syntax, we just showed above that if you kind of check for a key that doesn't exist, it's going to throw an error. If you were to do that in a default dict, well, then it has a default associated with that key. And so now, if you're kind of to check if this exists, it's going to show you that it's a default dict where the default is an integer, and this is your real hash map or dictionary there. Basically, when we put this over here, it automatically made the key value pair of 2 to 0. So I won't spoil the fun, but there's kind of cool things you can do with that, particularly if you were to make this a list. If we were to run this again, it's going to make it map over to a list, and that one comes up pretty commonly in LeetCode problems. Now we'll finish this off with a really cool dictionary, which is basically called a counter, and it just basically counts the elements of the thing you're given it. So we would do from collections, you would import capital counter here like that, and if you had a string, so I think we still have that one called string. So basically this one has multiple A's, B's, C's, and E's, and one of the most common patterns in data structures is to count the things that you have. Now if you wanted to count the frequency of the elements with a normal dictionary, you could definitely do that, and you could definitely do it with a default dictionary as well. But what's really cool is you could actually just immediately make this with, we'll do lowercase counter is a counter of the string, and if you were to print what that is here, you would see that you basically have a dictionary that shows you all the different key value pairs, where the keys are the things that you have, and the values are the number of occurrences in that thing that you count. So it quite literally counts the stuff that you gave it. Now I probably wouldn't recommend counters in an interview. I feel like it's a little too much of a Python cheat. Default dictionaries are probably okay. They're kind of just a little bit better than dictionaries. But if you want to be the most safe, then I would probably just use the standard dictionary that they're given. This is the one that's most like a normal hash map. Okay, guys, so you can get this code in the description if you want and play around with this. I hope this was helpful. Drop a like for the win.
Okay, nice. So let's begin with ransom note. Right. This is my account. Okay. So given two strings, ransom note and magazine, return true if ransom note can be constructed by using the letters from magazine and false otherwise. Okay, so ransom note is A. Okay, so ransom note. Okay. So I given two strings ransom note and magazine, return true if ransom note can be constructed by using the letters from magazine. Okay, so I'll just put them in the set, right? And then I'll simply check if this is in this, right? So I'll say our set equals set of ransom note, and mset equals set of what is our magazine. First I just want to print them, right? Print our set, print mset. For now I'll just return true, and let's run it. I think that's a capital, yeah, sorry, my bad. True. Okay, you are submitting too frequently, please try again. I just want to run it. Okay, right, so I had, okay, so now I want to check if the key, okay, so I will loop through for x in um, let's say M set in the magazine if um, um, if xn, let's say R set, right, then it's okay. If x, let's say not in R set, then we return false, else we return true if this is correct, right? Okay, so now I was expected true. Oh, right. So I want to do it other way around. I will go for x in Ransom note and x in M set, magazine set. Okay, now I am wrong here. So we have ransom note AA and magazine is B. Right. So for X we go ransom note, right? X if X not in M set we return false. Um, let me just print ransom note and note. Okay, so here magazine. Okay, now I was right for X in R set, so it should have been just a single element, then if X not in is A not, no, it should have just returned true, expected false. Oh, okay, because A and B and there is A. All right. So this string, okay, A and B, so it is kind of a counter, right? Okay, so set would not be right here because it is basically counting it, right? So using the set I can create a um, the easiest would be the counter but I don't want to do that. So right, I get it because simply we need to check how the number of A's, like there was a single A and a single B, so obviously we cannot convert B from A. Then there was a single A and a single B, but there are two A's, right? Right. Okay, so this problem revolves around the availability availability of the availability of the alphabets including their size, right? Including their size. So I can construct like I have created two sets, right? Then I can create two more dictionaries. I'll say addict so I will go for X um, for s in ransom note, right, I want to look through it. um, Ransom node, I want to create this. For s in ransom node, I have let's say our dict is an empty dictionary right now, and magazine dictionary is an empty dictionary right now. So we have ransom node, so our dict of s, okay, I can make it a default dict, right? I had learned about default dictionaries, and default dictionaries are great. Let me just check.
Are so common in Python and data as a default. If you were to
Okay,
pass,
so
say,
from collections import default dict, right? So I can just go here and import from collections import default dict. Did I do it right? From collections import default dict, and then default dict, then this can be a default dict of type int, right?
the type of integer.
Yeah. Okay, so it will store values of type int, and then we have another default dict of type int. Okay, so I can say plus equals 1, and that's basically it. And similarly for s in magazine, I can have dict plus equals 1, right? So I just want to print these first. This is working, right? Okay, unsupported operand collections dot default unsupported operand type for and some node equals construct from collections import default dict, from collections import default dict, right? Okay, but okay, if I go counter, right, then I go counter of ransom note. Well, this is cheating. But for the sake, I get it. See, what I have to do is magazine. But let's see. This work, yeah. Counter is A1, then we have A2, B1. Okay, so I get it. I don't need this. I'm just going. I'm just going to use simple dictionaries. Dict. Oh, sorry. Empty dictionaries. I want to make a counter. we will go if Sn rdict, if the key exists, then we will go rdict of s plus equals 1, else we go rdict of s equals 1. And I want to apply the same logic here. If s in mdict, then mdict of s plus equals 1, else magazine dictionary of s plus equals 1. Let's try that. Okay, B, key error B. At line number 17. Yeah, I checked if S is in. Oh, sorry. My bad. 1. Okay. There we go. Okay, so we get a counter. Right. Now, I just want to check if in the magazine. Okay. Then we are creating counters for the numbers. Right. Magazine. Okay, O of n solution. Then it's again a for loop for let's say x n if x n, also for x n magazine, if x n are dictionary, and we want to check if again it's in dictionary and it's in dictionary so if x in dictionary and I say m x in dictionary rdict of x is greater than or equal, sorry, is less than or equal to then it's okay, else we return a false. Right, is that right? If arcs in rdict, okay, so I just yeah, because this condition is false, so it returns a, yeah, okay, so we will just flip the condition and we want to return false. Will it still throw the error? Yeah. If x in R dictionary. Yeah, it is not. B output is true. Oh. right? So if the letter if x in our dictionary, then false. Okay, so we'll go if x not in okay, I feel like I should check the other way, right? For x in ransom, right? Because we are basically checking about the ransom. So if x in mdict, right? If it is and okay, if x not in m dictionary, simply return false. Then and else if it is in if dictionary the number of letters are less than or equal to the number of letters x, then it's okay, right? Then I will just make it a little neat. Okay, so I get this, I get it true. Okay, for x here, if x not n x not n, then we return false. Okay, so we get this. Oh, sorry. Yeah, we return false. Both these conditions, yes, right. Okay, let's try and submit it. Then I will. Yeah, right. Okay, so I did get it, but it's not the best solution. But I feel like because it is wasting time constructing this. Right. Okay, we'll take a look at it later. For now,